All right, so let's look at our low frequency response. So our fully biased common collector amplifier is going to look something like this. So here's our supply voltage VCC and our resistor R1. Here we have our resistor R2, our input capacitance Cin, our signal resistance R sig, and then we apply our input at this terminal over here. Coming out this way, then we're going to have our amplifier itself. So connected to the emitter terminal, we're going to have some resistance Re, as well as our output stage, which is just a capacitance C out in connected to a resistance RL, like so. Our output voltage is measured at this node. And then our collector is tied directly to ground. Now, I want to mention something here. When we analyzed this circuit in 335, I drew it slightly differently in as much as I effectively only had a resistor R1, R2 wasn't there. The only modifications that's going to make is everywhere we had, I think what I called RB, just treat that as R1 in parallel with R2, and now it's the same damn thing. This is just a more formal description. So like we've done every other low frequency response, we can break this amplifier up into 3 discrete stages. So everything to the left of this dashed red line is our input stage. That's going to have a transfer function of Vx over Vin, where I'm going to put that voltage Vx here directly at the base. Our output stage is just going to be this capacitance and resistance that we have connected between the emitter node and ground. So this is our output, which has a transfer function of V out over Vy. So I will define Vy to be the voltage directly measured at the emitter node. And then everything in the middle is the amplifier stage, which has a transfer function of Vy over Vx. Okay. The mid-band gain of the amplifier stage is given by Gm times R naught in parallel with Re divided by 1 plus Gm R naught in parallel with Re. This relationship should be in your notes from 335. So now let's look at what's going on with the amplifier stage. All right. So for our amplifier stage, we would have something akin to this, okay? So I'm going to put just my voltage Vx here, which is the output of the input stage. So we'll sort that out in a little bit. Here is my base terminal. I have my resistance R pi, my voltage VBE like so. Here's GM VBE. Here is R naught. My collector is grounded. And then over here at my emitter, I have my resistance RE, and the voltage drop across this resistance is the voltage Vy, but we can't forget that our output stage is going to effectively load this thing as well, so it's going to contribute to the frequency response of the amplifier stage. So that's just going to look like an impedance of RL plus 1 over SC out in parallel with RE. So I'm just going to modify this to, instead of being an RE, let's just call it a ZE, where ZE comes out to be, so that's RE in parallel, bless you, with RL plus 1 over SC out, or RE times 1 plus S RL C out divided by 1 plus S RE plus RL C out. So this to me looks pretty much like the standard common collector amplifier configuration, except that everywhere that we would have had RE, or realistically, so let's notice something here. Common collector amplifier is one of my favorite to analyze because the analysis with channel length modulation and without channel length modulation are effectively exactly the same, because the resistance R naught can be thought of as just in parallel with the resistance RE. So if we were to ignore that resistor R naught entirely, do all of our analysis with channel length modulation ignored, at the end, we would just, everywhere we have RE, put it in parallel with R naught, we'd get the exact same result. So anyway, so I think that this is going to look, or the transfer function for this stage is going to look something like this. So we'd have Vy over Vx is equal to GM R naught in parallel with ZE divided by 1 plus GM R naught in parallel with ZE. So we can expand on this, and I'm not going to make you guys suffer through all of the steps by any stretch of the imagination. I'm just going to give you some intermediate steps and then hit you with a result. So we could expand this out to look like GM times R naught ZE over R naught plus ZE. Divided by 1 plus GM R naught ZE over R naught plus ZE. Close that, make that not quite as long. And from here, it should be fairly straightforward to see how we would get something like GM R naught ZE over R naught plus ZE plus GM R naught ZE. So this would literally just be multiplying this one by R naught plus ZE over R naught plus ZE, canceling out the common denominator of everything, and then lumping stuff together, right? Nothing, no huge amount of algebra going on there to get from this step to the subsequent step. This form would allow us to directly substitute in our expression for ZE, and then that's where the algebra gets really, really gross. And so what we're going to wind up getting is, so let me put after, that's not how you spell after. After lots of algebra, we wind up getting Vy over Vx comes out to be GM R naught in parallel with RE over 1 plus GM R naught in parallel with RE times. So my denominator is going to be the gross part here. 1 plus S times R naught in parallel with RE plus R naught times RL over R naught plus RE plus RE RL 1 plus GM R naught all divided by R naught plus RE. That whole thing, sorry, that line got away from me. 1 plus GM R naught in parallel with RE. That big ugly resistance multiplied by C out. And then my numerator is a nice 1 plus S RLC out. So we have our midband gain taken out. We've got a pole and a zero, exactly like what we should expect. So that's our amplifier stage in a nutshell, where I skipped maybe half a page of it. Not horrifying to get there, like some of the other ones are. For our output stage, we effectively have this network. So here's our voltage Vy, effectively the output of our amplifier stage. Here's a resistance Re, a capacitance 1 over SC out. A resistance RL, and here's where we're taking our output voltage. This is literally the exact same voltage divider network that we have seen with all of the other output stages of our low frequency response. So it behaves exactly the same way. So V out over Vy is S RL C out divided by 1 plus S RL C out. So we get a pole, excuse me, we get a 0 at 0, and the pole here actually cancels out the 0 from the amplifier stage. And again, we saw that in the common emitter amplifier and all that kind of good stuff too. Output stage, easy peasy. Okay. Input stage, another place where the math gets really, really gross. So we will skip a lot of things. So for our input stage, we have a network that looks something like this. So here's Vn, then we have the resistance R sig in series with 1 over SCN. Here's R1 in parallel with R2. Here's our voltage Vx. And then we have this resistance here, which I'm going to call Zn prime. And this is just the resistance or the impedance looking into the base terminal of the amplifier stage. So Zn prime is nothing more than R pi plus one plus beta ZE, where that ZE is the exact same impedance ZE that we talked about previously. Okay? So nothing particularly wild or crazy there. Once again, it just looks like a voltage divider because everything looks like voltage dividers except for the amplifier stage. And so the ratio of Vx to Vn is just going to be R1 in parallel with R2 in parallel with Zn prime divided by R sig plus 1 over SCN plus R1 in parallel with R2 in parallel with Zn prime. And after an absurd amount of algebra, this winds up looking like S times R1 in parallel with R2 times Cn times R pi plus 1 plus beta Re in parallel with R naught plus S times R pi times Re in parallel with R naught plus RL plus 1 plus beta Re in parallel with R naught times RL. Let's see, so close that bracket. C out, close bracket. There's our numerator. Hold on just a second. I can't draw this and think at the same time. Lamy, what were you asking? No, so just to be clear here, so all of this part together is the resistance, and then all of that is what's multiplied by S. So I believe I have the correct number of brackets, right? So this bracket right here is closed by this bracket right here. This one right here is closed by this one on the outside. So I split it up in that way so that we could see the S times R1 in parallel with R2 times Cn is giving us one of our zeros. And then that whole large second term is giving us our second zero, where it's just going to be this bit right here divided by all of that part right there as our other zero. So that's our numerator. And then our denominator is once again a second order polynomial, where A is equal to R1 in parallel with R2 times R pi times Re in parallel with R naught plus RL plus 1 plus beta, RE in parallel with R naught times RL. And I'm coming down to the second line here because there's more to come and I won't be able to fit it all on one line. Sorry, actually, I need to close this bracket here. Sorry about that. R sig times R pi plus R1 in parallel with R2 times RE in parallel with R naught plus RL plus 1 plus beta RE in parallel with R naught times RL. Close that bracket, close the curly brace, multiply by Cn times C out. So that's the coefficient of our S squared term in the denominator. B is going to be R sig times R pi plus R1 in parallel with R2 plus 1 plus beta RE in parallel with R naught plus R1 in parallel with R2 R pi plus 1 plus beta R naught in parallel with RE all of that times Cn plus R pi plus R1 in parallel with R2 RE in parallel with R naught plus RL plus 1 plus beta RE in parallel with R naught times RL. Close that times C out. And lastly, C is R pi plus R1 in parallel with R2 plus 1 plus beta RE in parallel with R naught. So from this guy right here, we obviously get 2 zeros and 2 volts. Exact same way if we've done it all of the other things. And once again, skipping pages of algebra because it adds nothing to the discussion whatsoever. All right, so that's our direct analysis. Now, let's talk about if we wanted to do the short circuit time constant method to estimate where our midband begins, what that would entail. Right, so this will be pretty easy. Yep. It is indeed a lot of parentheses. Lots and lots of parentheses all over the damn place. All right, so short circuit time constant approximation. So we only have two capacitors to deal with, C in and C out. So let's look up here really quickly and kind of see what C in is going to see. Okay? So I believe that C in on the left-hand side is just going to see R sig. On the right-hand side, it's going to see R1 in parallel with R2 in parallel with whatever we see looking into the base when C out is a short circuit. Right, which means everywhere that we see RE, it's now also in parallel with R. So from that, so let's see. So Cn will see. So here is our capacitor. Over here, we have our resistance, R sig. Here we have R1 in parallel with R2. And this is the resistance looking in. It's no longer going to be an impedance because that capacitor is assumed to be a short circuit. So RCN is simply R sig plus R1 in parallel with R2 in parallel with one second. Oh, nope, I'm looking at the wrong thing. That's why I'm confusing myself. My apologies for that. R pi plus 1 plus beta, R naught in parallel with RE in parallel with RL. Yes, ma'am. We're doing low frequency analysis, so only coupling and bypass capacitors. When we do the high frequency analysis is when the internal capacitors. So in the high frequency, okay, let me recap things. Let me go to way down here. If you're asking this, I'm sure other people are confused as well. So in general, our frequency response curve is going to look something like this, right? Where let's just call this guy right here omega low. And let's call this cutoff frequency over here omega high. So in the low frequency regime, coupling and bypass capacitors are transitioning from looking like open circuits at DC to short circuits once we hit the midpoint. Okay? We're at a frequency low enough to where all of our internal capacitances still look like open circuits. So because we're at low frequencies and all of those internal capacitances are so small, they don't even show up in our low frequency response because they're all still open circuits. Once we get to our high frequency analysis over here, this is where we're dealing with the effects of internal capacitances. And we are well beyond the frequency at which all of our coupling and bypass capacitors appear at work. So, yeah, so in the high frequency analysis, C in, C out, and then you bypass capacitors. You have look like short circuit. In the low frequency analysis, C mu, C pi, and CS all look like sleep. So, okay. Okay, then. So we've figured out what C in can see. The only thing that's even a little bit of a curveball is the RL being in parallel with R not parallel with RE. Everything else is exactly what we would expect from our simple DC analysis. Okay, so for C out, let's look at what's going on with C out. Scrolling back up here. So to the right, we're just going to see that resistor RL. That's pretty straightforward. Looking to the left, we're going to have RE. I'm going to call it RE in parallel with R naught. And then we're going to have whatever we would be looking up into the emitter terminal, making a note that I already lump R naught down here in parallel so that I don't count it effectively. So I would express that something like this. So this is the resistance that we see looking up into the emitter terminal. Here we have R naught in parallel with RE. This is the left-hand leg of our capacitor. Here's the right-hand leg of our capacitor. Over here we see an impedance RL. We're looking in here to find RC out. And so RC out is just RL plus R naught in parallel with RE in parallel with R up. So now we've got to figure out what that R up thing is. So I'm going to look at my small signal model. I'm going to call this resistance right here RB. So this is just whatever resistance we have that's connected between the base terminal and ground. So that is going to be R1 in parallel with R2 in parallel with R sig. Okay. Here's our base terminal. Oh, sorry, that should not be GM R0, that should be GM VBE. Brain fart, my apologies. Again, I'm not including R0 here because it's already taken care of by being in parallel with RE. And then here at the emitter node is where I would apply my test source. So we can analyze this, I believe, pretty quickly here. So I can say that the current IX is flowing into node E. Current GM VBE is flowing into node E. And there is a current of Vx divided by R pi plus RB flowing out, where let me just explicitly say here, RB is R sig in parallel with R1 in parallel with R2. So I can find VBE just using voltage division because I have a voltage source and then I have a series combination of resistors in parallel effectively with that voltage source, right? So VBE is nothing more than negative Vx times R pi over R pi plus RB. Okay with that? Good old voltage division, nothing wild or crazy there. And when we substitute that in, so I could write this as Ix is equal to Vx over R pi plus RB plus Vx times GM R pi divided by R pi plus RB. Anybody got beef with my algebra there? I'm going to pull that Vx term out. And so that's going to look like 1 plus beta, because GM R pi is nothing more than beta, divided by R pi plus RB. And from here, the resistance that I called R up is just the ratio of Vx Ix, which is R pi plus RB over 1 plus beta. And so now putting everything together, we have RL plus R naught in parallel with RE in parallel with R pi plus R sig in parallel with R1 in parallel with R2, all divided by 1 plus beta. So that's our low frequency response. Direct analysis. So I was going to say no assumptions were made there, but technically there was one assumption that was made, but it's actually the assumption that we made calculating the gain of that circuit way back in 335. We made an assumption that R pi was greater than 1 over GM. That's the only assumption that was made in our direct analysis whatsoever, which should always be true. All right, so let's look at our high frequency response, and we're not going to get very far into this because the notes I have are very, didn't get as far as I wanted to. Okay. So common collector amplifier, high frequency response. So I'm going to start by drawing my circuit with all of my coupling and bypass capacitors shorted out. And then on top of that circuit, I'm going to superimpose my high frequency capacitances, just like I've done with every other high frequency response that we've looked at, right? So here I have VCC and my resistance R1. Here's my resistance R2. Cn is a short circuit, so all we're going to see here is R sig. Here is RE. C out is a short circuit. So now we're just going to see RL directly connected to that. We're going to measure our output voltage here at the emitter node directly now. And once again, my collector node is tied to my supply voltage. right? So that's what everything looks like with all of our coupling capacitors sorted out. Now, we should have a capacitance C mu between the collector and the base. We should have a capacitance C pi between the base and the emitter. And we should have a capacitance CCS between the collector and ground. So from an AC perspective, where our supply voltage is considered an AC ground, that capacitor CCS is connected to ground on both sides. So this capacitor does not show up in our high frequency analysis, which is great. So it can arguably significantly easier. Our capacitor C mu is just going to be connected between the base and ground, right? So we are going to refer that capacitance effectively over to the input side of things, because ground is ground. It doesn't matter if we treat it as if it's at the collector or elsewhere. And then that C pi is going to be in parallel with the resistance R pi. So our small signal representation of this circuit should look something like this. So here's Vn, R sig, here's R1 in parallel with R2. Here is C mu. There's where I'm choosing to put my base terminal. It's fine there. Here's R pi, dBe. And directly in parallel with that guy, I'm going to put C pi. Here's GM, keep doing GM R naught, and it should be GM dBe. Here's R naught. My collector node is grounded. And I'm just going to use this node right here as my emitter. And so between my emitter and ground, I see RE in parallel with RL, and my output voltage is here. So what I'm going to do to analyze this thing is I'm going to make a couple of simplifications. The first thing that I'm going to do is I'm going to replace everything to the left of this dashed red line with its 7 and equivalence. Then I am going to lump these guys together and just call that an impedance Z pi. And I'm going to lump these guys together and call this just RE prime. So let's look at that stage to the left of the dashed red line, right? So we have Vn R sig R1 in parallel with R2. 1 over SC mu. And we're taking, sorry, that should say V Thev. Our Thevenin voltage with respect to ground. So to me, unsurprisingly, this looks like yet another voltage divider network. So I'm going to say that V Thev is just Vn times the ratio of R1 in parallel with R2 in parallel with 1 over S C mu divided by R sig plus R1 in parallel with R2 in parallel with 1 over SC. And looking at this network as a dead network, you could find a Thevenin equivalent impedance. What do you guys tell me what that's going to be? Everything's in parallel. Yes. So just R sig in parallel with R1 in parallel with R2 in parallel with 1 over S C. Absolutely. All right. So now I am going to introduce the 3 simplifications simultaneously into our small signal model to see what shakes out. And so what we're going to have is our Thevenin voltage in series with our Thevenin impedance. Sorry for putting an R there. Here is our base terminal. Here we have an impedance Z pi over which the voltage drop VBE occurs. Here is VM VBE. And between our emitter and ground, we have an impedance RE prime. And this is where we take our output voltage to be. So we can effectively consider everything to the left of this dashed line, our input stage, and everything to the right of this dashed line, a combination of our amplifier stage and our output stage blended together, effectively, right? So let's define a couple of things here really quickly. Z pi is nothing more than R pi in parallel with 1 over SC pi. So that should be R pi divided by 1 plus S R pi C pi. RE prime is R naught in parallel with RE in parallel with RF. So if we look at our amplifier stage, yep. So if we look at our amplifier stage by itself, so I'm going to call this voltage right here Vx, just like I have done in previous times. So the voltage at the base, we're just calling this Vx. So that's going to look something like this. So we have Vx as an input voltage, which is dependent on our input stage. RE prime, V out. EMVBE. What does this thing look like? Just a simple common collector amplifier, except that everywhere that we would have seen R pi, we would replace it with Z pi, and everywhere we would have seen RE, we would replace it with RE prime. So from 20 minutes ago, the transfer function for this stage, V out over Vx. So this is going to be GM times, actually, I'm just going to put it as, because I don't want to take the RE out of it, or excuse me, the R naught out of it, because it's already lumped in there with RE prime. GM RE prime over 1 plus GM RE prime. There is effectively no frequency dependence whatsoever on the amplifier stage of this thing. Now, realistically, it's showing up that way because of the assumption that we made that R pi is much greater than GM. Now we're making an assumption that Z pi is much greater than 1 over GM, which should still probably be valid. So it's all going to work out okay. This has R naught in parallel with RE already buried inside of it. So really the only thing that we would have to do to this stage right here to pull out our midband gain is take out that factor of RL. So this should look something like, actually, I know what it's going to do in the numerator, but I'm not 100% sure of what it's going to do in the denominator. So I'm going to leave it like this. I think this will be roughly okay. We've just got that extra RL in parallel, but that's just going to be some DC thing that's going to lower the gain by some small amount. All right, just because I don't want to waste you guys' time doing algebra in front of you that's not particularly difficult. Okay, so for the input stage of things, and this is where I'm running out of notes, so we'll probably just set this up and call it a day. So we effectively have our Thevenin voltage, our Thevenin impedance, the impedance looking into the base, and here's the X. Okay. So our transfer function for this guy is going to look like Vx over Vthev is simply Zn prime over Zthev plus Zn prime, where Zn prime, so again, this is just the impedance scene looking in now. So earlier, let me scroll up here. Vn prime looked like R pi plus 1 plus beta Ze. Now it's going to look like Z pi plus 1 plus beta Re prime. Right? Give me Re prime. And that's where I ran out of notes. So sometime between now and Friday, I will burn through this algebra. I'll bring this back up and I'll put in pulling the midband gain out of the stuff from the amplifier stage and flesh this out into something that looks normal and will give us poles and zeros. We'll finish that up in a tight 5 to 10 minutes, and then we'll move on to bigger and better things. All right. Thank you, guys.